Hi everybody, my name is Anthony Sanchez, and today I'm going to be talking to you about gaps of saddle connection directions for some branch covers of tori. So I want to give a special thanks to the Nearly Carbon Neutral Geometry Topology Conference for giving me a chance to talk about some of my work, and especially to Jane Wong for inviting me to this mini session on moduli spaces of surfaces. Okay, and so let's get into it. So I want to walk us through the construction of kind of the main character of the rest of the talk, something that I've been calling doubled slit tori. So I want to show us how to construct one. So the first step is to just take a flat torus and mark 2 points on it, right? This is not saying anything fancy. You grab your favorite parallelogram in the complex plane, identify the top with the bottom, and then the left with the right, and go ahead and label 2 points on there. So I'm always going to label the vertex of the parallelogram, and I'm going to call it dot, and then I'll label some point on the interior, and I'm going to call it x. And right under the identifications, dot is like a single point, even though in the picture it's 4 points. And so what I want to do now is take an identical copy of the twice marked torus, as so, and then go ahead and cut a slit between the 2 mark points. And now that we've kind of opened up the 2 tori, I want to kind of close them back up by identifying opposite sides of the slit together, right? So if we're on the left torus, I want to identify plus. Now with the right torus on the now with the bottom of the slit of the right torus. Okay, and this is a double slit torus. Maybe the name makes sense now. We've taken a torus, we've doubled it, and then we glued it along the slit that we cut. So double slit torus. Maybe it's very easy to see too that kind of based off the construction, there's going to be a genus 2 surface, right? Each kind of individual torus is going to contribute genus 1, and we've created no other holes through our construction. And there's going to be 2 cone type singularities of angle 4 pi, right? And this is just saying if I'm standing at either x or I'm standing at dot, and I try to put a Euclidean ball about me, I'm going to see two Euclidean balls about me, each with angle 2 pi, and consequently with total angle 4 pi. Right, and so I've done this here for x, but something exactly the same thing will happen if we do this at dot. Okay, so that's what a double slit torus is, and I'm kind of interested. In paths on these double slit tori. All right, and so maybe a natural question is, why am I interested in double slit tori? Well, topologically, they're a very natural construction of a higher genus surface from genus 1 surfaces. And the study of genus 1 surfaces is prevalent in kind of, in many areas of mathematics. Dynamically, these are interesting because they've provided the first higher genus surface that has a minimal but not uniquely ergodic straight line flow. This was kind of a geometric interpretation of Maser of some work done by Veach previously. And so I won't define these words, right? This is kind of dynamical motivation, but what I'm saying here is the following. If I'm standing on one of these double slit tori, there exists some direction so that if I start walking in that direction, then I'm going to see both tori. That's kind of what minimal means, but I'm going to spend more time in one torus over the other, and that's kind of what uniquely ergodic means. And then the main reason why I'm interested in double slit tori is because they constitute examples of translation surfaces, and I'm trying to study some kind of fine scale behavior of certain paths on translation surfaces. Okay, so let me kind of unwrap a little bit what I mean by translation surface. What I mean by translation surface, right? So how do we create a double slit torus, right? We started off by embedding them in the complex plane and then identifying sides with the translation. Well, translations are holomorphic functions, and so consequently the quotient is going to be endowed with a Riemann surface structure that I'll call x, right? And so what else lives on the complex plane? dz lives on the complex plane, and dz is preserved by translations. Consequently, the kind of resulting quotient is going to have a holomorphic differential given by dz as well. Okay, and so right, this kind of allows us to do geometry, right? We're able to kind of measure lengths of curves. We're able to compute angles now, and more generally, any pair x omega, where x is a Riemann surface and omega is a non-zero holomorphic differential, is called a translation surface. So double slit tori constitute an example of translation surfaces. And again, the holomorphic differential is what allows us to kind of do geometry. Gives us, a way to measure length, sense of direction. And so overall, what I'm very interested in doing is I'm interested in paths on double slit tori. And so here's an example of another double slit torus, in case you wanted to have another example in mind. And I'm not interested in all paths on double slit tori. I'm interested in certain special paths on double slit tori, and I'm going to indicate to you why I think they're very interesting paths to kind of restrict to. Okay, so the paths that I'm interested in are called saddle connections, and these are just straight line trajectories that start and end at a cone type singularity. So as an example, you know, here gamma is a saddle connection indicated by the purple line that starts, say, in the bottom left torus, crosses through the left torus, goes around the left torus once, crosses through the slit, pops out of the next torus to the right, and then winds around the right torus 2 more times before coming back to where we started. And now this is kind of the point of the holomorphic differential, right? We're able to kind of use the holomorphic differential to get some geometry out of these curves and associate to each curve the holonomy vector, right? So I have some path gamma, I have dz, and so I integrate it, you know, I integrate dz along the path, and I'm going to get kind of like the direction and the length of the path. And in this case, I'll get 4 plus I. I guess this is kind of assuming that, you know, the sides of this parallelogram are 1. But we see in the left torus, I'm going to go around the left torus 1 time. In the right torus, I'm going to go around the right torus 2 times horizontally. And then, so that's a total of 3 units in the horizontal direction. And then the last bit is going to come from kind of combining the piece of the saddle connection that goes through the slit. That's going to give me another unit contribution. And then I've gone up once. So the holonomy vector in this situation is going to be 4 plus I. And if I wanted to, I could easily think about this as the vector 4, 1. That's a perfectly good way to think about it too. And so as another example, maybe we have here this bread curve delta that's going across the top of the left torus, right? So it's going up and it's not going up and down at all. And we kind of agreed that the side of this parallelogram is going to be 1. So the holonomy of delta is just going to be 1. Or said another way, it's going to be the vector 1, 0. Right? And so I can do this for many, many more paths, right? There's lots of saddle connections that we could, you know, kind of draw on these double slit tori. And for every single one of these saddle connections, I can go ahead and track how much I go in the horizontal direction and how much I go in the vertical direction. And this is going to give me some vector inside of R2. Okay? And, you know, in this case, the 2 vectors that I'm going to get here is going to be 4, 1 and 1, 0. So now let's look at all of the holonomy vectors on a double slit torus. Okay, in which case, kind of generically, you're going to get some picture that looks like this. And I'm kind of saying that this is kind of the right picture to think about by a theorem of Veach. Veach shows us that the holonomy vectors is a discrete subset of R2, or of the complex plane. And right, every check here kind of indicates, you know, how much some saddle connection on the translation surface has gone over in the horizontal direction and in the vertical direction, right? And so now that's great. Now we have this discrete subset of R2, and all the questions that we kind of have classically, you know, asked about the integer lattice, we can ask about this discrete subset. For example, you know, a very natural question is, you know, what are the expected number of points inside of a ball of radius R for some holonomy vectors? And more generally, any question about the integer lattice can be asked about this discrete subset given by holonomy vectors. And now this isn't some arbitrary discrete subset, right? This is a discrete subset that's somehow kind of keeping track of the geometry of certain paths on a translation surface. So this discrete subset is like a very interesting discrete subset as it's tracking kind of the paths on the translation surface, the saddle connection paths on the translation surface. Okay, and that's what one motivation why one may like to study holonomy vectors. And kind of my focus in this project has been, you know, how random are the holonomy vectors for double slit tori, right? So we start off with a double slit torus. On here, there's saddle connection paths. For each saddle connection path, track its holonomy, and you're going to get some check inside of R2. How random is this set? And of course, this is a mathematics lecture, so everybody read the slide like this, and for good reason. You know, what do I mean by random? So I'm going to walk us through kind of 2 notions of randomness. So kind of the first maybe test of randomness that one could ask is to look at the angles of a double slit torus. You know, are there any forbidden angles that, you know, if I'm on a cone point, and are there any kind of forbidden angles for which I can't, you know, go from one cone point to another point? And that's all that I mean by angle, right? Grab the saddle connection, kind of project it onto the unit circle, and then see what shows up. And kind of the first result in this direction was given by Mazur, who showed that angles are dense for any translation surface. Okay, so right, this picture should have kind of more red in it than black, but I've only drawn a few of the saddle connections, and so if I draw more and more of them, they're going to start to fill up the circle densely. All right, and so that's great. There's no forbidden angles. We're kind of seeing everything on the unit circle. Are there any kind of special favored angles? Or not? And I guess this kind of question is asking about the equidistribution of angles of translation surfaces. And this was addressed by Vorvets, who showed that angles are equidistributed for almost every translation surface, which is kind of to say, which says, you know, angles are being kind of distributed about the unit circle with the right proportion. So if I have kind of like a big interval in the unit circle, then I'm going to see lots of angles showing up there. And if I have a small interval, then I'm going to see less, right? They're kind of uniformly distributed, is what Vorovets' results showed. And the upshot of these two results is to basically say that saddle connection directions are behaving randomly at first glance. Okay, right? They're going everywhere by kind of Mazur's result, and not only are they going everywhere, but they're kind of going everywhere with the right proportion. This is kind of Vorovets' result. And so we're mathematicians, and so for us, one test is never enough. And so we want to consider a second test of randomness. And it's very common in mathematics to kind of have an equidistributed sequence, and then to kind of look at the gaps of this equidistributed sequence and ask about the behavior of that, to look at the gaps of equidistributed sequences. Okay, and so I'm going to kind of change my philosophy a little bit, and instead of looking at angles of translation surfaces for kind of dynamical reasons, I'm going to look at slopes of translation surfaces, but they're not so different. Right, you know, we can get from one to the other by taking an arc tangent, and so kind of information about one is going to pass as information for the other. Okay, and so now let me just be a little bit clear about what I mean by slopes of holonomy vectors. So let slopes of R of holonomy vectors denote the set of slopes inside of this little eighth sector here, right? So the holonomy vectors are a discrete subset of R2, and this little eighth sector is a nice compact subset. And so there's going to be finitely many holonomy vectors that show up. So now that there's finitely many of them, let's go ahead and order them according to their slopes, right? So here I have S sub 1, and the next slope bigger than this one is going to be given by this holonomy vector with slope S sub 2, then S sub 3, dot, 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 up to however many there are. And that's what N of R is kind of indicating here. So kind of more formally, let slopes of R denote kind of what I said. It's just the set of, you know, increasing slopes. And N of R is just the number of slopes that I'm seeing inside of that region. Okay, and how many slopes am I seeing in that region in and of itself is a very interesting question, and this was addressed by Eskin Mazur, who showed that asymptotically the number of points in there is going to look like R squared. Okay, and so now here's like a good point to kind of, you know, recall what we've done in the past few slides. We started off by looking at angles of translation surfaces inside of the unit circle. And now we're switching over to slopes, but only inside of this eighth sector here. So it seems like I've lost some generality. In fact, if I wanted to know about slopes in some other sector, then I can kind of rotate that sector, kind of flip that sector into here, into this one, and then apply kind of the techniques that you see today to get information about slopes in that sector. All right, so there's really not too much loss of generality and kind of switching over to this eighth sector. And then I won't say too much about it today, but kind of there's a dynamical reason why we switch into slopes in this sector, and it's because there's going to be some renormalization that appears that makes looking at kind of points in this sector very good for us. So that's all I'll kind of say as to why I'm considering the sector. At any rate, we're mathematicians, and we always say one test is never enough. So kind of angles and consequently slopes are kind of well understood. And I want to look at a second order notion of randomness given by the gaps of the slopes. And this was the whole point actually of the last slide, right? To kind of order them, because now when I'm talking about the gaps of holonomy vectors, all I have to do is look at, you know, gaps of consecutive elements, is differences of consecutive elements, right? That's all that I mean by gaps of the slopes. And so now one thing we should kind of keep in mind here, I guess, is that as R gets bigger, the number of holonomy vectors that I'm seeing in this region is going to kind of increase. And in particular, the slope differences that I'm seeing are going to start to tend to 0. And so I want to kind of keep track of how big the gap was, at least at the level that I was looking at it in. So it's very natural to scale up by the number of slopes that I'm seeing inside of this sector. And the number of slopes that I'm seeing inside of this sector was given by Esk and Mazur and shown to be about R squared. So I'm going to kind of scale up that way, this gap, that way the gaps kind of are not tending to 0 as R tends to infinity. And so kind of my focus is, what can we say about the distribution of gaps, right? And so now the gap distribution is given by, grab the gaps of the holonomy vectors and ask how many of them land inside of our favorite interval I. Let's go ahead and count them. Now that we've counted them, how many of them could have landed in there? Well, that was n of R. That was the way we defined n of R. And now I don't just want to look at kind of gaps of holonomy vectors up to level R. I want to look at all of the holonomy vectors. So I want to let R tend to infinity. And this is the gap distribution limit of a translation surface. Here I haven't used anything special about double slit tori. This is just the gap distribution of a double slit torus. And there's, this is kind of trying to measure the proportion of gaps in an interval I, okay? And so there's lots of natural questions that we can ask about this, right? What can we say about this limit? What do we expect to say about this limit? So now I want to kind of turn our attention to what we expect in this situation. So if we can take some context from probability, and we can suppose that x of I is a sequence of IID random variables that are uniformly distributed on 0, 1, right? So I kind of take a random number between 0, 1, call it x1, take a second random number, call it x2, take a third random number, maybe it's close to the origin, call it x3, and so on. And so now the sequence of IID random variables is gonna partition the unit interval into a set of gaps, right? I see a natural gap between 0 and x3 given by this red region here, this red kind of pointers here. I see another gap arising between x3 and x sub 1, and then another one between x1 and x2, and x2 and 1. And so this IID sequence is going to naturally give us a certain gaps of the unit interval that I'll call gaps of x sub I. And so there's a kind of a normalization that's going on here that's not super important, but that I should make note of. And now we're kind of in the same position that we were with holonomy vectors, right? I have gaps of an IID sequence, and I want to ask, what can I say about this gap set, right? Or more generally, like, how likely am I to land inside of my favorite interval out of how many kind of points could have landed in there? And in this situation, the gap distribution for an IID sequence is going to tend to an exponential distribution, right? Which is just to say the following. If I want to know what's the likelihood that I'm going to have gaps that land inside of my favorite interval I, all I have to do now is integrate the function 1 over e to the x against that interval I to find out that proportion. All right, so this is kind of what we would expect from a truly random sequence. And kind of the big takeaway here is that the gap distribution of almost every double slit torus is not exponential, right? So what have we done kind of so far? We started off with double slit tori, and we started looking at saddle connection paths on there. Each one of these paths is going to give rise to one of these checks here on the right side, corresponding to how much I've gone in the horizontal and how much I've gone in the vertical direction. And kind of at level, at a first test of randomness, this is a random set inside of R2, right? The angles are kind of equidistributed. The angles are kind of dense on the unit circle. And we want to kind of look at a second kind of test of randomness. And that second test of randomness is to kind of look at the gap distribution of the slopes. And so if I look at it from the point of view of the gap distribution of the slopes, then there's some kind of underlying structure that's kind of preventing me from being a random set. In particular, it's preventing me from being an exponential function, all right? And this is going to more generally come from the following result, where I compute a density function for the set of gaps of double slit tori. So kind of this density function, right, was playing the role of the function 1 over e to the x from the IID case. So if I want to find out the proportion of gaps, inside of some interval I, all I have to do is grab my density function and then integrate that against the interval to find that out. And the picture to the right here is actually a graph of the density function f, right? It's a very wild graph, but it's a nice piecewise analytic function with 3 points of discontinuity. it kind of starts off, very constant, goes up, and then kind of jumps down. And so I want to kind of unwrap this density function a little bit and describe kind of what kind of corollaries we're able to obtain using the fact that we have an explicit density function. And one kind of natural question in this direction is to look at the gap distribution, is to kind of look at the tail of the gap distribution. And this is kind of asking, what is the probability that I'm going to see a big gap, say a gap bigger than size t? Well, then that just means I'm going to grab the interval from t to infinity. And now that I have a density function, I just integrate my density function against that interval t to infinity. And in this situation, I'm able to show that asymptotically, the tail of the gap distribution is going to look like 1 over t squared, right? So the probability of seeing a big gap, a gap bigger than size t, is about 1 over t squared. And I'll compare this to the IID situation. Right there, we had like an explicit density function as well, and in that case, we're actually able to integrate the density function against t, from the interval t to infinity, and in that case, we're going to get e to the negative t. So, which is to say the following: large gaps are unlikely for double slit tori, but they're still much more likely than the random case, right? We kind of have a heavy tail in our situation. And then on the other end of the spectrum, we could ask about small gaps, right? What's the likelihood that I see an arbitrarily a gap of arbitrarily small size? Well, that just means I grab the interval now, instead of from t to infinity, from 0 to epsilon, where epsilon's a really tiny number. And in this case, no matter how small epsilon is, I'm always going to see something. I'm always going to see a gap inside of that interval, no matter how small epsilon is. And now I should say that this is actually somewhat expected, since double slit tori are not lattice surfaces. And by result of a Theorem, there's a characterization that says we have support at 0 if and only if you have support at 0 if and only if you're not a lattice surface. And kind of the generic double slit torus is not a lattice surface. So kind of generically, we're going to have support at 0. Okay? And then maybe one kind of final direction that we can kind of take this to is, well, double slit tori are nice genus 2 translation surfaces, but there was nothing particularly special about their construction, right? We grabbed 2 identical tori and we glued them along a slit. We can do the same thing with d-identical tori, right? So let me go ahead and take d-identical tori and glue them along a slit in the following manner, right? If I'm here and I'm kind of moving around, I enter 1 and then I come out into the second copy. And then maybe I go up and I enter the slit here, and now I'm inside of the third copy, and so on and so forth, right? And so translation surfaces constructed in this manner have a name. They're called symmetric torus covers, and it turns out that symmetric torus covers have the exact same gap distribution as double slit tori, right? But symmetric torus covers can have, we can take D to be arbitrarily large, and so this is kind of computing the, an explicit gap distribution for a translation surface of arbitrarily high genus. And that's all that I kind of want to share with you guys today. So I want to say thank you. I want to give a special thank you to my advisor, Jayadev, who kind of introduced me to a lot of these interesting mathematical ideas. And then a special thank you to the Nearly Carbon Neutral Geometry and Topology Conference and the Moduli Spaces of Surfaces mini session. Thanks.